So there was one topic we didn't cover last time, if you remember, and that is, well, let's just start here. So if we have a container with water with red food coloring in it, so it looks something like that, right? And then all we do is we dilute it. So how do we dilute something? You guys know what that means? Add water, right? And when we add water, it looks like this, right? Not quite as red. You following? All right. So we're talking about dilutions here. Diluting. And so over here in the red food coloring, the high concentrated solution, we have a number of moles of red food coloring, yeah? How many number of moles do we have over here in comparison? It's the same. All we did was added water, right? Are we good there? All right, so let's see. Here we have, which one do we have a higher concentration? The red one or the pink one?
Red.
The red one's higher concentrated, right? So we can say that's M1, our concentration 1. Remember, molarity is capital M. You guys good with that? And over here we have concentration 2. Good? And over on the left we have volume 1, and over on the right we have volume 2. And I can call this N1 and N2 as well, right? But we do know that N1 equals N2. Do we understand what I'm talking about so far? Okay. Now, if I take a concentration, M, just in general, we know that's moles per liter, right? Number of moles per volume. You with me? Now let's multiply both sides by the volume. And we get the number of moles is equal to the concentration in molarity times the volume. Are we good? All right. So what equation can we form from here? N equals mv. What should we say N1 is equal to? M1 times V1, right? And that's equal to M2 times V2. You all following me? Questions? Ladies and gentlemen, all I did was derived this equation. You don't want to have to worry about that. Just write it on your note card and you got it, right? Or if your note card's too full and you understand what I just did, you can do it on your own, right? Your call. That kind of makes sense? All right. So we use this to find out a few things. We can calculate a new concentration from our given values here. Or we can calculate a volume if we know our concentration, right? We can solve for any one of those. Good? All right, so now let's do a real problem. So let's say we're doing an experiment, and we need hydrochloric acid to mix with something, and we want to know what happens if we change the concentration. So we're doing a little research, and we, okay, what if I take a half a molar concentration of hydrochloric acid and mix it with this aluminum? What's it going to do, right, for example? And so we go to the store to find half a milliliter concentration of hydrochloric acid. Then we buy a bottle. Then then we say, okay, what if we increase our concentration to 1 molar solution? So we go to the store and buy a 1 molar concentration of hydrochloric acid to see what it does to our aluminum, right? And we go and go and go, and we find a lot of different concentrations. And pretty soon we have a whole shelf that's clear full of these different concentrations of hydrochloric acid. Then next week we're going to do it with sodium hydroxide. We're going to run out of room real quick, right? So what do we do instead? We buy a big bulk bottle of high concentrated solution of hydrochloric acid, and then we make our own. Then we just have to buy 1 bottle. Isn't that nice? Okay? Yeah, that's what we do. Okay? So let's say we have our 12 molar concentration of hydrochloric acid, and we want to make 500 milliliters of 0.5 molar concentration of hydrochloric acid. Okay? How are we going to do this? Well, we're just going to use this formula. Okay, M1 V1 equals M2 V2. What's M1? What should we say M1 is? What we start with. That's a good thing to say, right? We started with our 12 molar concentration, so that's M1. What should we say V1 is? Whatever volume of this that we use, right? We don't know that yet, do we? And what should we say M2 is? Yeah, here's our M2. What does that make this? Our V2, right? Now, can I flip-flop those and say this is my second solution and this is my first solution? Does it matter? Yeah, it doesn't matter, because we can just flip those around and it's the same, right? So I like to start with whatever I start with is my first, and whatever I end with is my second. Makes sense in my mind. Are we good with that? Okay. All right, so what are we looking for here? Our V1. Okay. So let's divide both sides by M1 to get V1 all by itself. So now our V1 is equal to M2 times V2 divided by M1. Now let's just plug our values in. Our M2, which is 0.5 molar, right here. And our V2 is 500 milliliters. Now, does that need to be measured in liters? What do you think? Let's find out. Let's find out. And divided by M1, which is our 12 molar concentration. What cancels? Molarity cancels, right? And we're left with milliliters. Is that okay if we have our volume measured in milliliters? Yeah. If we want it in liters, then we can convert it. If it doesn't matter, we can just leave it there. So it doesn't matter if we're in liters or milliliters, or even centimeters cubed, right? Whatever. All right, so we do that. What's a half times 500 divided by 12? Can somebody do that for me? 20.8 milliliters of a 12 molar concentration of HCl. Are we done making our 500 milliliters of 0.5 molar solution? No, what do we do now? Add what to it? Water. We're diluting it, right? So here's our high concentrated stuff. Not very much of it, right? And then we're going to add water. How much water? Until we get to 500 milliliters. If we want to know the exact number, 500 subtract 20.8, right? That gives us 479.2. So we're going to take this and we're going to add 479.2 milliliters of water. Make sense? Or no? And do another one? Yeah. Okay.
Can we do the first one
On the worksheet?
Yeah.
Yeah. Let's do it. Okay, it says, calculate the following dilution quantity. It says, how much water would you need to add? So we're looking for how much water. How much in grams or milliliters or what? Probably milliliters, right? Because we're going to add this to 100 milliliters of a 0.5 molar concentration of sodium hydroxide. And we want to create a concentration that is 0.150 molarity of sodium hydroxide. So we know what we're looking for, and we know what we know. Now where to start? What are we doing? We're adding water, so what are we doing? We're diluting it, right? So we have to use the dilution equation. M1V1 equals M2V2. Since we know we have these variables, what should we do next? Determine which one is M1, which one is V1, which one is M2, which one is V2, right? Okay. What's our first solution? This one here at the top. So this is our V1, and this is our M1, right? Does that make sense to everybody? Or am I just talking? We good? Okay. And what do we call this? That's our M2, our second concentration, right? So what are we missing in this formula? V2. Okay, so let's do this. We're looking for V2, so let's solve for V2. And we get V2 is equal to M1 V1 over M2. Let's plug our values in. We got M1 is 0.5 molar, and V1 is 100 milliliters over our M2, which is 0.150 molar solution. Molarity cancels out, leaving us with milliliters. And we get 333.3 repeating milliliters. Is that right? So is that our answer?
Yeah, then we have to subtract 100 milliliters from it.
Well, why is that?
Because we added water.
Yeah, we want to know how much water we add to this in order to make this, right? Yeah. So if we started with 100 and we end with 333, how much did we add? 233.3 milliliters of water. So ladies and gentlemen, make sure we answer the question that it asks. And don't just, oh, we have an answer, there it is. That's a common mistake people make. Okay? We good? Do you want to try the other one on your own? All right. Do it. Yeah, we're adding it to this. Uh-huh.
Okay, so I threw myself. So, okay, so 12 is on M1, V1, and then I just did and I was solving for the V2, which should be there.
Yeah, that's it. That's it.
That's it. Okay.
Yeah. How are we feeling? Yes? No? Do we want to go over this one? Okay. All right, so it says how many milliliters? So we're looking for volume, right? Volume in milliliters of 0.5 molar concentration of HCl can be made by adding water to 25 milliliters of 12 molar concentration of HCl. So where's my first solution? Does it matter? It really doesn't. It really doesn't matter. Okay? But if you're going with what you start with, what are we starting with? We're starting with this and we're adding water to it, right? So we can call this my solution 1, and this right here is my solution 2. Good? All right. So this is going to be V1. This is M1. This is M2. This is V2. Are we clear with that step? Okay. And so we're looking for V2, right? Are we looking for how much water we're adding? We're not. We're just saying we're adding water to this, so how much of this are we going to make? Right? So M1 V1 equals M2 V2, and we're solving for V2. Divide M2 to both sides. And we got V2 is equal to M1 V1 over M2, which is equal to M1 is 12 molar concentration, V1 is 25 milliliters, divided by M2, which is 0.5 molar concentration. See that the molarity cancels, and that gives us 600 milliliters. Good? Questions? Yeah, Ren.
I set my problem up that exact way, but I'm not getting 600. I don't know if I'm calculating it wrong.
So you actually wrote it in the formula this way?
Yeah. Oh, well, I mean, I had the moles flip-flopped, but that doesn't matter, right?
So let's say we said this is V2 and M2. Is this what you did?
No, I did 25 as V1, and then I did 12 as M2, and then 0.5.
Okay. That does matter.
Okay.
Yeah. So it says we have 25 milliliters of 12 molar. That means that is one solution. I don't care if you say that's solution 1 or that's solution 2,
Okay.
but it has to be the same solution.
Okay.
Does that make sense?
Yeah.
Yeah, I made the same mistake.
But it doesn't matter which one is solution 1, which one is solution 2 out of the two solutions.
Okay.
Good?
Just as long as the full one solution
Is together.
they're both the same number.
Yep.
Like V1 and
Yep.
M1. Okay.
That's
that
right.
makes sense.
Good, I'm glad that come up. Good? Because if it comes up in class, it might not come up on the test, right? And then we'll be good. Are we good with dilutions? All right, that was the last part of last lesson. Let's move on to more concentration units. And we only have 2 more and then 1 more topic. And then that's all we have tonight. And if we have time, we can go over the study guide. And I do have more paper study guides. I sent it out to you because when I brought them here, it was Halloween and most of you wanted to go trick-or-treating, so I'm just kidding. With your kids probably, but okay. We good?
Can we do the first equilibrium?
The equivalent?
Yeah.
We will when after we learn it. Sound good? All right. So the first concentration unit that we're dealing with today is equivalence. What the heck is that, right? So in your area of your field, sometimes we worry about, well, maybe we have a pregnant mom and her iron level is not right, yeah? That's going to cause problems. So we got to know how much iron is in her blood. So we get a blood sample, and we just send it to the lab, right? What do they do with it? Well, they might measure how many equivalents there are. How do they do this? Well, so we might not care about equivalents, but it's kind of like doing moles. Can we measure moles in the lab? No, we can't. We just use it to convert it to what we're looking for, right? So it's kind of like that, okay? So here's how we find the equivalent, and this is just going to be a conversion factor we can use to convert to what we're looking for, okay? So for example, we might want to know, okay, how much iron 3+ is in blood. Well, to do this, one equivalent is equal to the molar mass of our ion that we're dealing with divided by the charge of that ion. Now, it's always the absolute value of the charge. What does absolute value mean? It's always going to be positive, right? That's all we have to worry about. So if we're dealing with a negative ion, we're just dividing by the value of that charge. That's it. It's not going to be, we're never going to get a negative answer. That's nice, right? Okay. And so if we want to find one equivalent of iron, and we'll just abbreviate it EQ, one equivalent of iron, 3+, is equal to what? What's the molar mass of iron? Somebody tell me.
55.85.
55.85 grams of iron, and then we divide that by, that's charges plus 3. Well, how do we know it's 3+, guys? Maybe we have maybe it's maybe that's the compound we're dealing with, right? But if we throw that in water, what happens? It dissociates because sulfate is soluble, right? It dissociates, and so it leaves us with iron and sulfate ions. Well, what's the charge of this iron? Do you remember how to do that? Sulfate has a charge of, do we remember that but without looking at anything? 2-, good. And there's 3 of them, so that's a total charge of -6.
The other side must be positive 6 to be neutral, right? Total of 2 of them, 6 divided by 2 is 3 plus. Are we good? That's just a review of how we might figure that charge out. Okay, if it's a transition metal. If it's not, then we just look at the periodic table, right? Okay? Any questions there? So that's going to equal, so if we divide that, we're going to get 18.61 grams of iron is equal to 1 equivalent of iron, 3 plus. We good? All right. So let's say when we collected blood from this person, we collected 1.20 milligrams of blood. Can we figure out how many grams of iron are in our blood? Or maybe, yeah. Yeah. No, let's not do that. Let's keep it simple. Let's say it's 1.2 milligrams of iron in our sample of blood, right? Sorry, I got a little carried away. How many equivalents do we have? Can we do this? We know what we're looking for, and we know what we know. We should always start with what we know. 1.20 milligrams of iron 3 plus. What are we going to convert to? Grams, because we know grams per equivalent, right? So 1,000 milligrams is the same as 1 gram. That goes away. And now we can go from grams to equivalents. 18.61 grams of iron 3 plus to 1 equivalent of iron 3 plus. And that gives us 6.45 times 10 to the negative 5 equivalents. Are we good? So it's just dimensional analysis from here, guys. The only difference is how to calculate this conversion factor, right? That's it. When I say that's it, I'm not saying it's easy. I'm just saying that's all there is to it. Okay? What if we want to know how many milliequivalents there are? Can you do that? Can we convert this to milliequivalents? Is that any different than converting liters to milliliters? No, it's the same. 1,000 anything is equal to 1 of that same thing, right? It's just the prefix, and milli means 1,000 of them, right? 1,000. Questions on that? So if you're gonna put something on your reference card, I'd put this on it, right? Make sure you can do that. Yeah,
So for example, if you were to find the equivalence of just SL4, since the charge is -2, you'd still just put 2 as a charge?
that's right.
Okay, even though, okay.
Yep, good question. Does everybody understand that question? So if instead we was find one equivalent of SO42 minus, that would be the molar mass of SO4, which is 32 plus 64, right? That's 96 grams of SO42 minus. And we're going to divide it by just 2. Not -2, just 2. And so that will be 48 grams per 1 equivalent. Good? Any other questions? Okay. Yeah, let's do an example on our worksheet on section 2. Let's do the first one together, and then I'll let you guys do the second one. How's that? All right, so it says a solution containing a sulfate ion. Oh, is this where you?
No, I just.
Oh, okay.
Since you did like the crossing the
Yeah,
charts,
yeah.
SL4 was up there,
Yep,
so.
perfect. All right, so so this one we kind of just did, right? So we can we just say 1 equivalent of sulfate is equal to 48 grams of sulfate? Right? Are y'all with me? So we kind of did that step already. All right, we want to know what is the concentration in milliequivalents per liter? If we have a solution of 0.025 molar solution of SO42 minus. Are we good? Okay. We know what we're looking for, and we know what we know. So we should start with what we know. 0.025, and should I just leave that as capital M? It's not very useful that way. Let's change it to what? Moles per liter, right? So 0.025 moles of SO42 minus per 1 liter of solution. Okay. What do we want in our answer? Milliequivalents and liters. So we're not going to get rid of that liters. We're going to leave that there, right? And we're going to change moles. What are we going to change moles into? Look at our mole roadmap and see what can we change it to? Grams, right? Either moles to something else or grams of that same substance. Oh, we want to go to the same substance, right? Because we know grams is equal to an equivalent, right? So 1 mole of sulfate goes on bottom so they can cancel. Are you all with me? And the molar mass, we already figured that out, is 96 grams of SO42 minus. Good? Can you all do this? Okay. So that goes away. And now we have grams. We use this one. We didn't use this yet. Can we use that now? 48 grams of SO4. Why do we put that on bottom? So the grams can cancel, right? To 1 equivalent of SO4 2 minus. Grams goes away. Are we done? No, we got to go to milliequivalents. So 1 equivalent is equal to 1,000 milliequivalents. You guys can do this, right? Because I'm just going through. Maybe I should ask you guys. You tell me. Okay. Equivalents go away, and we're left with milliequivalents per liter, and that's what we're looking for. We're done. So we multiply and divide those, and we should get 50 milliequivalents per liter of SO4 2 minus. We good?
Professor?
Yeah.
So when we go back to the 1 equivalent of SO4 2 minus equals 48 grams, that's the molar mass?
No, that's the 1 equivalent. That's what we just barely learned about. So 1 equivalent is equal to the molar mass divided by the charge.
Okay, that's right.
Good? And we kind of did that right here. The molar mass of sulfate was 96, and the charge of sulfate is 2.
Okay.
No, thanks for asking. We good there? Do you want to try the next one on your own? Do it. Anybody wondering about discussion points?
Yes.
Okay. I kind of dropped the ball on that. So, should we just say everybody gets them?
Please.
I'm sorry. And maybe for an online class, this is great, yeah? So, I apologize if I added stress to you. We'll just kind of make that a case like, good? Okay, one other thing is, I never talked about the extra credit assignment for last unit. Anybody still wanted to do that, you can. Don't have to, but if you want to.
Was it the ice cream one?
Yeah. What?
That was for
Oh, you did it?
yeah, I
Good.
went to this place where the ice cream was nitrogen.
Yeah, that's cool.
It was crazy.
Daddy daughter date to go to Friday.
Oh, good. Oh, that'd be fun. Anybody need more time? Okay. Okay, yeah, let's do it. You guys ready to do it, or who wants more time by themselves? No? All right. So it says normal blood contains 3 milliequivalents per liter of magnesium 2+. How many milligrams of magnesium 2+ are present in 100 milliliters of blood? All right. We know what we're looking for, and we know what we know. So let's start with something that we know. Which one should we start with? Which is the easiest? 1 unit, right? Here we got units all over the place. Let's just do 1 unit. So let's start with 100 milliliters of blood. What can we convert to? Yeah, what does this mean? Milliequivalents per liter of blood, right? So we got to convert to liters so that we can eventually get rid of liters, right? So 1,000 milliliters to 1 liter. We use that one. We're not going to use that one anymore. Can we use this one yet? 1 liter is equal to 3 milliequivalents of magnesium. You with me? So liters goes away. Hold on a sec. I want milligrams. How can I convert milliequivalents into mass? I need to find the equivalents, right? So 1 equivalent is equal to what? Molar mass of magnesium, which is 24.31 grams over 2, because that's the charge. Good? So that's going to be 12.155, is that right? 12.155 what? Grams, right? So, okay, that's equal to 1 equivalent. So what do I convert this down here to? To equivalents, right? What goes on bottom? How many?
3, right?
Well, does milliequivalent cancel equivalents? No, so we want 1 equivalent on top, right? How many, what goes on bottom? 1,000 milliequivalents. Are you with me, guys? So milliequivalents go away. Now we have equivalents, now we can use this, right? 1 equivalent goes on bottom, so it cancels. What goes on top? 12.155 grams. Are we done? We got to go to milligrams, right? Not too bad, it's just an extra step. 1 gram is the same as 1,000 milligrams. That's it. So we got 1, 2, 3, 4, 5 conversion factors. Whew. But the majority of those we're converting to milli to regular, right? And we learned that the first week of school. Right? Questions?
Can I show you how I walked through the way I did it?
Yeah.
So I started with the 3 million equivalents
Yeah.
over
So,
liters.
good. You don't have to start with what I started with.
Yeah, and
Okay.
so then I went through, but then I was stuck with having to convert from liters to milliliters. All the way at the end though, so liters is on the bottom,
Uh-huh.
so. But I can't do 1 milliliter equals 1,000 milliliters, or 1 liter, cause then liters is on the top, since liters on the bottom, does that make sense?
Oh, okay.
I don't know
So
where to go
it's
from there.
flip-flopped, right?
Yeah,
Well, it shouldn't be. So if we started with, you started with 3 milli equivalents.
yeah,
Did you put per liter right here?
no, I just put liter underneath it.
Okay, good. Per 1 liter,
And then I converted to 1 equivalents, or, or.
1,000 milli equivalents
Yeah.
to
1.
1 equivalent, good.
And then I did the 1 equivalents equals the 12.15, yeah.
Okay,
And then I
Grams.
went to grams, yeah.
and then what?
I went to 1 gram equals 1,000 milligrams.
1 gram is 1,000
And then
milligrams.
I still have to convert to milliliters.
Okay, so we
that's
have-
where I'm-
We have milligrams here and we have liters here. So we still didn't use this.
Mhm.
So let's convert liters to milliliters. So 1 liter is the same as 1,000 milliliters, right?
Yeah,
That goes away. And then can I just times by 100 milliliters? Because that's how much blood I have, right?
yeah.
Well, it has to go on the bottom. Nothing.
Okay,
That's it.
I was just,
So do you see that it doesn't matter? So these are all being multiplied or divided. Does it matter the order we put these in? A times B times C is the same as C times B times A, right? It doesn't matter the order you multiply. So, yeah, that's okay. But that's why I start with the simplest, because then I can just keep going one step at a time and I don't get one unit clear over here that's not, right?
yeah.
But if it makes sense in your mind, yeah, it doesn't matter.
It makes sense both ways, I just picked the mill equivalents just cause
Yeah.
I knew I needed to convert off the bat.
Okay.
For the
Yeah.
other, just a single one, so
So what's the best way to do it?
whatever works.
The way that works in your brain. Yep. Good. We good? Anything else? All right, let's move to the next unit of concentration.
What was the answer?
Oh, the answer was 3.65 milligrams of magnesium 2 plus. All right, let's go on to osmolarity. Y'all remember what molarity is, right? How do you calculate molarity? Moles of solute over liters of solution, right? So osmolarity is almost the same. Okay, we see the word molarity in there. What is the os for? What does it sound like in biology?
Osmosis.
Osmosis. You guys know about osmosis? Okay. What is it? Some weird sciencey crap? Okay. But you guys are, well, I don't know if you'll use it personally, but if you're dealing with somebody with kidney problems, kidney failures, they do dialysis, right? So you have this dialysis tubing that I'm guessing, I've never actually done it, but the blood goes through this tubing, right? And what do you do with this tubing? You put it in a solution, is that right? Okay, what does it do? What is the purpose of that? Does anybody know? Kind of like filtering your blood a little bit, right? Cleaning your blood or whatever. How does it do it? You don't have to know. I just want to know if you know. So it allows the particles to transfer through the tubing to the other solution that's in there, or vice versa, wherever it's going to go. I'm not sure which. I think if it's going to clean it out, then the particles go from the blood out to the other solution, right? Is my guess what happens. And well, what allows that to happen? The number of particles in the solution. Okay. So depending on how many particles you have, it's going to allow it to go quicker or just not at all. Okay. I'm not going to go more in depth than that. If you want to learn about osmosis, you can. But you guys have a reverse osmosis system in your house for your water? Okay, we won't go there. All right. So osmolarity is equal to the molarity. So it's still going to be moles of solute over liters of solution, right? Times the number of species dissociated. What does that mean? So if we have a container of water, let's say, and we throw sodium chloride in it, what happens? Do you remember? It dissociates into sodium and chloride. You with me? So how many species dissociated? We got 2. So this went into 2 species. If you like that word, I don't know if I like that word. Or, okay, two particles, right? And so that's what we're talking about. So if we let's do an example here. Let's say we have 1.05 moles of magnesium chloride in 3.5 liters of solution. We want to calculate the osmolarity. Okay. So we know osmolarity is equal to molarity times the number of species. So let's find the molarity. Start there. We think, are we good with molarity? How are we going to calculate it, guys? Somebody tell me. How many moles? Well, we have 1.05 moles of our solute, which is MgCl2 in this case, right? Over amount of solution, which is 3.5 liters of solution. So there's my molarity right there. Now I got to multiply this by the number of particles dissociated when I throw this magnesium chloride in the water or this in the solution. How many particles am I going to get? 3. Magnesium, we got 1 magnesium ion, right? And 2 chlorine ions. Total of 3. You with me? So we're going to multiply that by 3, and we're going to get 5.38, we call it osmol. Good?
Yeah, I definitely hate species for that though.
Oh. Is that the right stuff? No, that's not really the right answer. I was looking at the wrong problem. 0.90 osmol of magnesium chloride. What's your question, comment?
No, I was just gonna say that makes me really hate the word species for that because it makes me think of like which, like two, like elements or
Oh, yeah.
particles.
So maybe we should just say particles, right? Particles dissociated. Good? Should we practice that a little bit? How many particles we have? So if we have copper sulfate, any ideas how many particles we have here? 2. There's no parentheses on our polyatomic ion. That means we have one of them, right? And then we have one of those. So that's a total of 2 particles. You following?
If our equation starts with grams, we have to convert grams to moles.
That's right. We got to get molarity first, which is always moles per liter. Yeah. So it could be given to you a number of ways, right? What about sugar? C12H22O11. How many particles do we have when sugar dissolves in water? Just 1, because it doesn't dissociate. It's a covalent compound. You with me? So if it's a covalent compound, it will not dissociate. So it might dissolve. If it's polar, it dissolves in polar, right? So sugar's polar, it's going to dissolve in water. Yeah, so that's just 1. Any covalent compound will just be 1 particle. That means the osmolarity of a covalent compound is the same as the molarity. Good? All right. You want to try one of these examples? Let's just do the first one. Or do you want to do... I guess they're all... It's just, let's do the bottom one on the right. So we have 0.0345 moles of ammonium chloride in 0.400 liters of solution. And we got to calculate the osmolarity here. So what are we going to do? Anybody? Somebody? Somebody? Find the molarity first, right? Moles per liter. We have moles and we have liters. 0.0345 moles of sodium or ammonium chloride over 0.400 liters of solution. Now we got to multiply the number of particles that dissociate. How many? 2. 1 ammonium, because there's no parentheses, and 1 chlorine. Good. And so we get 0.173 osmol. Good? Can you do these? Do you want to try one on your own or move on? No comment? So how you feeling? If we want to spend more time on the study guide, we can move on. If you'll want to practice this and forget about it, or whatever, right? What do you want to do? No one has opinion? That's okay. All right, let's move on. But if you want to go over it, please say something. All right, let's talk about the last topic for tonight, for this unit, and that is colligative properties. All right, so colligative properties is a fancy word of saying what happens when, sorry, how you can elevate your boiling point. So boiling point, elevation, or melting point or freezing point, depression, meaning it goes down, right? And there's also one with vapor pressure. You can change the vapor pressure with this as well, but I'm not going to have you do that one. A little bit more in depth, okay? So, where is this used? Well, it snowed today. Did you guys catch that? Ugh. That means pretty soon there's going to be ice on the roads. That's fun, right? So what do we need? Salt. We put salt on there. Does anybody know why we put salt on the roads? It lowers the melting point. Well, how does it do that? Because we put the salt in the solution of water, right? It dissolves into different particles. So the more particles it dissolves into, the lower it's going to bring the freezing point. So if it lowers the freezing point, that means if it's 0 degrees Celsius outside, and then we just lower the freezing point to -1 degree Celsius, that means it's not frozen anymore. Goes liquid, it melts and we don't have ice anymore. Nice, right? So that means it gets colder. What else we use this for? We make ice cream, right? You guys ever make ice cream with homemade ice cream? We used to have a machine that you'd have to turn like this. Mom, can my brother do it now? My arm is tired, right? Okay. I don't know. But anyway, how does that work? You put the salt, you put the ice in there, then you put the salt, more ice, salt. Well, it just makes it get colder. Colder than freezing. So it makes ice cream better. Good? All right. So it has to do with what? Osmolarity. Has to do with the number of particles that's dissolved in the solution. Same thing with boiling. You put salt in your food. What does that do? It elevates the boiling point. What temperature does water boil at? You guys know? At sea level anyway. 100 degrees Celsius. Okay? And so if we put salt in our water as we boil it, it's gonna take longer to boil. That means it's gonna cook our food hotter. therefore get done quicker, right? We good? So therefore, when you're making a pot of soup, just put tons of salt in it, right? No, I'm just kidding. All right. So let's just figure out how much our melting point might lower, or how much our boiling point might raise. Okay, so let's do an example. So the boiling point of water, so we're dealing with water here. Whoops. And the boiling point of water increases by 0.51 degrees Celsius per mole per liter. What? Per mole per liter. What's moles per liter again? Molarity. That means 0.51 degrees Celsius per molarity. But it's really something else. What is it? Per osmolarity. So we can say 0.51 degrees Celsius per osmolarity. Why osmolarity? Because it's determined by the number of particles in our solution. Good? All right, so let's say we want to know what the boiling point is if our water contains 8.56 grams of lithium chloride in 75 milliliters of solution. Where do we start? Well, we see this. Can we find the molarity of this solution? The osmolarity? Yeah. So concentration is always amount of solute over amount of solution, right? So 8.56 grams of lithium chloride, that's our solute, over 75 milliliters of solution. Is that molarity yet? No, let's convert it and get it to molarity. What are we going to convert first? Doesn't matter, just pick one. What? Grams to moles, perfect. We got to have moles. So what is our molar mass of lithium chloride? Lithium has a mass about, I can't remember that one. Is it 9? 6.9, so 7. Plus chlorine is 35.5. So what is it, 42.5? Did I do that right? Grams of lithium chloride to 1 mole of lithium chloride. That goes away. Now we have moles per milliliter, so we need to convert milliliters into liters. So milliliters goes away. Now we have moles per liter. That's great, but we want osmolarity, so what do? Multiply by the number of particles dissociated in water. How many? 2. Lithium chloride is just 2. Everybody okay with that? So that's going to give us 5.38 osmolarity. What? We good? And now we have this conversion factor to find out how many degrees it's elevated, right? So 1 osmol on the bottom, so it cancels, to 0.51 degrees Celsius. Osmolarity cancels, and we're left with degrees Celsius. That's great. And we get 2.75 degrees Celsius. Is this my final answer?
Kelvin?
If it wants. But is this my final answer? Let's look. What's the question? Let's go back. What is our question?
Final boiling point?
Oh, is this the boiling point of water? Uh-huh.
Subtract 100.
Yeah. Do we subtract or do we add? Well, we have, this is boiling point elevation, right? When we add particles, it raises our boiling point. So we're going to add that to 100. So we have 102.75 degrees Celsius.
So you're saying adding 100 because it's saying H2O increases, so that's how you know you need to add because it's increasing?
So water boils normally at 100 degrees Celsius.
Yeah.
So boiling point always increases by increasing the number of particles dissolved. So that's why we add that. If we was talking about freezing point,
Then it's
it would lower, right? Make sense? Okay, we have about 30 minutes left. Should we try some examples here? Okay, let's see. We have one that they're both boiling points. So I guess that's probably all you need to know, I guess. And besides, I will give you that 0.51 degrees per osmolarity, right? That'll be given to you. You don't have to know that. All right, which one do you want to do? First or second one? You do the next one. First? Let's do the first one. If the boiling point of 1 liter of water is raised by 0.51 degrees Celsius for every mole of solute added. So this is 1 liter, so it's every mole per liter, right? But anyway, so it's always going to be per osmol. So really it's 0.51 degrees Celsius per osmol. Good? What is the final boiling point? So that's basically the same thing we did, yeah? On the next one, just another one of the same things. So yeah, let's just do this. So we have 350 grams of C2H6O2 in 1.5 liters of water. Okay. First step is find the osmolarity. To find osmolarity, find molarity, right? Good? So the molarity is 350 grams of our solute, C2H2O2, over our solution is 1.5 liters. Good? Yeah.
They have H6, but I don't know.
Oh, did I write that wrong? Yeah. I just read my handwriting incorrectly. Thank you. Yeah, is that going to make a difference? Maybe or maybe not, we'll see. But yeah, thank you, appreciate that. All right, so grams per liter, so what do we gotta convert?
To moles.
Grams to moles, yeah. So we find the molar mass, so 1 mole of C2H6O2 has a molar mass of 62.07 or 08, whatever.
07.
Grams of C2H6O2, good. Grams cancel. So now we have moles per liter, that's molarity. To find osmolarity, what do we multiply by?
It's gonna be 3 now.
3?
Well, on this one, because you have 3.
Yeah, what? How many particles?
3
How do you know 3?
carbon, hydrogen, and oxygen.
Be careful. What kind of compound is this?
So it's covalent.
This is covalent. So how it does not dissociate. So how many particles?
1.
Just 1. So write that down in your notes, highlight it, bold it, whatever you got to do. If it's a covalent compound, it will not dissociate. Only ionic compounds do. And that's if it dissolves, right? All right, so really it's just, there's our molarity, which is equal to the osmolarity. And so that is Whoa, 3.76. And then we can use this here, 0.51 degrees Celsius per osmol. That goes away, and we end up with 1.92. So what's my answer? What am I looking for? What's the boiling point? 101.92 degrees Celsius. Good? All right, then section 6 kind of throws stoichiometry in there. You want to try one? Okay. First one's good enough? Okay, we have, says, what is the volume? We have 16 molar solution of nitric acid. We want to know how much would use to react with 5.5 grams of potassium hydroxide. According to this equation, HNO3 plus KOH gives us H2O plus KNO3. What kind of reaction is this? Acid base, good. Okay. All right, what's our first step? Balanced equation, good. Don't forget that step. Can you balance it by yourself? Bet you could. What coefficients do we need? It's already balanced, right? It's all balanced. Good. Okay, that step's done. Now, where should we start? We want to know the volume of, we want to know the volume of, of the 16 molar solution? So, should we start here? Because that's the simplest piece. What do you think? That's where I would start. What can we convert to? Look at our mole roadmap. Grams to what? Moles. That's the only thing we can convert to, right? And the molar mass is 56.11 grams of potassium hydroxide to 1 mole of potassium hydroxide. Now what do we convert to? We got to find volume of what? HNO3. We got to go to a different substance. So what do we use? Mole to mole ratio, right? What's the mole to mole ratio? Oh, they're all ones, right? Okay. So 1 mole of potassium hydroxide to every 1 mole of nitric acid. That goes away. Now what? Well, we used 5.5. We're not going to use that again. Can we use this yet? This is moles of HNO3 per liter of solution, right? Yeah, we have moles of HNO3, so can we put 16 moles on the bottom? Does that make sense to everybody? To 1 liter of solution? And that's what we're looking for, volume of solution, right? We're done. Multiply and divide those, and we get 0.00613 liters, or we can say 6.13 milliliters, right? How are we feeling, guys? Doing okay? No? What's up?
Probably the last 3 months.
Sorry.
It's not your fault.
Oh, I'm teaching it, so maybe it is. Are we good at dimensional analysis yet? Okay. A lot of it here, right? Okay, that's it for tonight. Do you want to, anybody take a look at that study guide? I emailed it to everybody because I passed this out during, I guess I already told you that. Anybody want a copy? 3? Yeah. Anybody else want one? For free. Okay. Does anybody have any questions on any of these? I don't know if you looked at them. So I know we're a real loud crowd, so a lot of talking. So if just we have one at a time, that would be okay. I'm just teasing. Sorry. And if you guys would rather just go home and look at it, whatever you need, I'm here. If you want to start at the front, because that was the furthest away. But if you're done, I'm done. Your call. If you want to go, you can go. If you want to stay and ask questions, I'll be here. Have a good one,
Thank you, Mr. Powell.
if you're going. But you guys know how I make this, right? So, look through it, if nothing else. Yeah, take care, Eugene.
A question with, the
Yeah.
notes the election notes. I was confused with this part. What did we do here?
So, remember a long time ago, we had to figure out the charge of this? Because the transition metals, we can't look at the periodic table and know what charge it is.
Right, because they're transition.
So this is 2 minus because it's sulfate,
Okay.
and there's 3 of them, so that's -2 times 3 is -6.
Oh.
And all ionic compounds are neutral, so this side has to be +6.
Oh.
Divided by 2 is 3 plus. But we didn't have to really do that because they gave us that.
Oh, the answer was right there.
Does that make sense?
Yeah. Yeah. Okay. Please
Okay.
keep studying.
Yeah, okay.
And I had another request.
Okay.
Do you know if it's possible if I can take the exam on Friday, like at the testing center?
Yeah, send me your email
Okay.
and I will set you up to do that.
Okay.
Can I do it?
Alrighty. I'll send you an
Can
email.
I take it Monday? Other testing?
No, yeah. Yeah, just send me your email and I'll get you set up.
I just don't have time to study during the week.
No, yeah.
Thank you.
Yeah, take care.
And then we're not meeting that Tuesday, right? I just Thanksgiving next week.
Oh, that's
Thank you.
right.
You.
Take care.
You as well.
Oh, that's coming up, huh?
Yeah.
Is it already there?
I think so.
Or do we have one more?
Is it one more?
Yeah, we have one more.
Okay.
One more week. But yeah, you can do Monday. Just send me that email so that I remember to set you up.
And then will they give us one of these or do we print one
Yeah, we'll give them to you.
at the test?
Uh-huh. Did you have a question, Alex?
I just don't get where we got the 100. Like, I got everything else, but
Okay.
I just
So
didn't
so
get
that's given information.
Okay.
Well, not it wasn't given, but we just need to know that the boiling point of water normally is 100 degrees Celsius,
Okay.
and the freezing point of water is 0 degrees Celsius.
Okay.
So that's I don't remember if that will be given to you. Let's see. Calculate concentration, lowest molarity, equivalence. Looks like it's not on here.
I'll just write it down.
So it looks like we're good.
I left my phone here last week.
Oh, did you?
Yeah, and then the highway patrol guys called me and my wife at like 2 a.m.
Oh, man.
We found your phone on campus, is everything okay? And I got my phone out.
It was okay until you called me and woke me up.
I found out that it was gone on my drive home, and then I came back and it was locked.
Oh, dang. And you left it in here?
Yeah.
Dang it. I didn't notice it. Sorry.
It was stressful. I really can't do my job without my phone.
All right, take care, Alex.
Have a good night.
What's your job again?
I do building maintenance at Health Theater, Sandy,
Oh, okay.
and Live Theater.
Does that mean you get free tickets all the time?
I get 12 season tickets as a Christmas bonus.
Oh, heck yeah.
I get lots of free tickets.
Nice. All right, take care.
And Beauty and the Beast, and it's like way behind schedule. We had to move
Oh, really?
I feel bad for the box office today, for all everybody.
Ah, dang. All right, take, what?
My daughter really loved it.
Oh, I bet.
We dressed up and,
Oh, heck yeah.
like last year we did the Little Mermaid. No, last year was out.
Oh, man. Now I'm jealous.